We're now going to look at how to build a resistor. This is similar to when we talked about how to build a capacitor. The capacitance of a capacitor, at least a parallel plate capacitor, depended upon the area of the plate and how closely spaced they were. Now, the resistance of a resistor also depends on the physical makeup of the object we're creating. So if we have here, again, a cross-section of wire of some length L, and we have cross-sectional area A, think of it like a tube where water is flowing down. The longer the tube, the harder it is going to be to push the water through, but the bigger the tube in diameter, the more water we can push through, so the easier the water will flow. The same arguments are made for electricity. So the longer this wire, the harder it is to push current through, but a large cross-sectional area makes it easier to push current through. It also depends on this new topic called resistivity. Now the resistance is for a specific resistor. Again, the symbol for resistor is just this jagged, shark tooth type design. Resistors have specific values, a 110 ohm resistor, 1.3 mega ohm resistor. What if we wanted to create a resistor with those specific values? Well, we can, depending on the material that we have, because if you want to build something that's a very good resistor, you might not want to use a very good conductor to do it. If you want to build something that has a very low resistance value, you need a good conductor. So, to calculate the resistance of the resistor, R, capital R, so that's the resistance of the resistor that's measured in ohms. It depends upon, it's equal to the resistivity of the material, that's this curly P, it's actually the Greek letter rho. This rho is the resistivity of the material. That's something you have to look up in a book. Different materials have different resistivities, but all materials of the same type have the same resistivity. For example, pure copper has a very specific resistivity. You can look that up in a book. Pure aluminum has a very specific resistivity. Pure iron has a very specific resistivity. Iron alloys, throw some tin in iron, mix it together, that will change the resistivity of the material. So, depending on what your wire is made up, what alloy it's made up, what materials are in it, it will have a very specific resistivity. That's something, rho, that you can look up in a reference book. Or of course, your textbook will have some simple examples. So, the resistivity depends on the material itself. The other two terms depend on how you make the material, the shape of the material. So the length is in the numerator here, so longer length means bigger resistance. And the area is in the denominator, which means it's inversely proportional. So a big area means a small resistance value. So if I tell you I have a meter-long copper wire that has a cross-sectional area of 1 millimeter, you could plug in all of that information and tell me what the resistance is of that wire. Now, resistivity does depend on the material, but there is a caveat. Resistivity is temperature dependent for most materials, which means that when you heat a material up or you cool it down, you change how well it conducts electricity. Typically, for most conductors, when you heat a resistor up, it actually becomes harder to push current through. The resistor value increases. So, this is something we can also calculate. The resistivity of the material is equal to some original resistivity at some given temperature. Usually it's 0 degrees Celsius or 25 degrees Celsius, where they define the temperature of the resistivity, plus 1 times alpha. Alpha here is the temperature coefficient of resistivity. That again is something you have to look up in a book. So copper will have a specific not only resistivity, but a temperature dependence on that resistivity. That's something you can look up in a book, or your book gives some examples of basic materials. times the change in temperature from whatever temperature rho naught was measured at. So for example, let's say rho naught was measured at 25 degrees Celsius. You want to know what the resistivity of the material is at 100 degrees Celsius. Well, you plug in the resistivity of the material at 25 degrees Celsius, multiply that by 1 plus whatever the alpha temperature coefficient is for that material, times the change in temperature. Well, you're at 100 degrees Celsius. Originally, the temperature was at 25 degrees Celsius, so the delta T here is 75, right? The difference between those two. So you would plug in 75 degrees Celsius, figure out what the new resistivity of the material is at that higher temperature, plug that in here to get the value for that resistor. So in a light bulb, an old filament light bulb, an old incandescent light bulb, there's a very thin piece of metal, usually tungsten or something, that has a very specific resistivity and a temperature dependence. When the light bulb is off, the material is cool, so its resistance value is different than when the light bulb is turned on. When the light bulb is turned on and current is flowing through the light bulb, it gets hot. That's why it glows and gives off light. Or think of the electric burners on an electric stove. When you turn your electric stove or your oven on high, you can see the burners glow red, the filaments. I'm not talking about a gas stove here or an inductive range, but an old electric range, old style electric range, or even modern electric ranges. So as they heat up, the resistance of those coils in your electric range changes. The resistance of the filament in a light bulb changes. And so that changed resistivity means a changed resistance to that material. So when you're designing something like that, or when engineers are designing something like that, they have to take that into account. So this is the relationship between resistance, which is a fixed value given in ohms, and the resistivity, which is material dependent.